Okay, good evening. So we will address the issue of floating point accuracy, as everything we are computing with such desire for speed is in fact floating point. So you have heard right, floating point. Despite the temperature, don't have any hallucination. It has to be enjoyed sparingly. We will turn to some more moderate on some poetic aspects. The Japanese people tell that their woodblock printing are image of a floating world, and we are to explore the computation in a floating world where many of our certainties will disappear. So I encourage you looking at the paper what every computer scientist should know about floating point computation. Much wisdom is in this paper. So we all have some knowledge of numbers, the real number, algebraic number, constructible number, decimal number, binary numbers, and floating point number. Are they not all the same? Not quite. We are also encouraged to think of it in this way, as there are primitive types in many of our languages, float, double, long double, quad, and recently half. So when computation don't turn out as expected, we'll explore what are the various errors that comes into play, rounding error, conversion error, propagating of error, and composition of error. We will need to have heuristic when things go wrong. If the computer is giving us wrong result, what can we do about it? How can we guess that he has made some extensive computation, it has made some extensive computation, and it is not quite what we expected. Maybe we will be so lucky to reach the point where we can speak about non-dimensionalization and formula entropy reduction on some other aspect late in the night. So floating point numbers are not something to be dismissed. The result of this computation that we do have effects. We have a moral and financial responsibility. In the 90s, some floating point error costed a problem with Patriot missile in the first Gulf War. So it's trendy these days, so who knows? Recheck your libraries. They made a 600-meter error for interception, 218 people killed and 100 injured in response. So don't use a floating point number to measure time. In the 80s, the Vancouver Stock Exchange accumulated error over 2 years, and their stock market index was so badly evaluated as to have a 50% error compared to what was expected. So I already mentioned the paper by Goldberg, and you have links to it. It says that floating point arithmetic is considered an esoteric subject by many. I hope that at the end of this talk, you will share this belief. So when we speak of floating point number, it's not so much a matter of language, because most of them provide us with the same format, IEEE 754. As Adrien described it, well, it's a kind of scientific notation with a normalized significance, and this normalization leads to numbers that are not immediate to represent. So we have a sign, we have some exponent and some mantissa. It exists as a single precision floating point number on 32 bits total, double precision over 64-bit total, including 53 bits of mantissa. There's a trick for the 53. The long double are not so popular, but you can see that for 40 years, everybody has paid for this functionality in their CPU, and hardly anybody uses it. Sure, it's not vectorizable, but it's cheap accuracy. 3 more decimal digits compared to double precision. When you are sure that all your program vectorizes nicely, you can, say, I don't need long double. But you may still need it for a slower pace and more accurate results. I like to say a lot of bad things about half precision floating point number. So here is the one of IEEE, and not the one of BrainFloat 16 from Google. But before this format, we had lots of them. Here is only one of the 3 pages of the link quadiblock.com, where you have the detail of all the floating point format that existed. So we owe a lot to Professor William Kahan, the father of floating point. He was a consultant at Intel when they designed the 87 floating point unit. And he was the one to push for this long double format inside the Intel chip. In fact, the Intel chip until of the 32 bits kind always evaluated calculus, any computation in long double, and then truncated the result. So when you move, if you still have some 32 bits processor, you will find that your results are slightly different. So his web page is also, albeit outdated, a very nice collection of paper where we can learn a lot and take a lot of examples. So I will not enter in the detail of all these numbers that you can use to represent, or you compute from the sign the shifted exponent on the mantissa, which is truncated. In fact, you have to imagine that there is always a 1, and that the binary separating point is here. So this number is 1.0 times 2 to the power 127 minus 127, which is 1. So as Adrien mentioned, we need a special representation for 0. When everything is 0, the standard representation breaks. And as long as we had to use a special representation, we also have a -0, which is useful for complex number computation, where -0 on the imaginary axis can change your function. We have a number to express infinity, which in fact means overflow, overcapacity, as well as the famous not a number when you try to divide by a 0 or take the square root of a negative. You already heard about the denormal or subnormal floats, and we will have some time to learn more about it. Okay, so if you want to represent your favorite number, you have a flurry of URLs here that will display it nicely. Please play with it. And in the same way, when you want to see what is the binary representation of your floating point number, you can do it with such a simple program in C. When you use this %A as a format for printf, it will express it. Your 1 will be 1 times 2 to the power of 0. And 2 gets 1 times 2 to the power of 1. And 3 is 1 plus 8 in hexa is 1/2. 0.8 is in fact 1/2. So 1.5 times 2 is 3. So from this representation, as I said, all these languages allow you to do it. So you have a nicer way to do it in C++ with the manipulator xfloat, and don't forget to return back to default float after. You get exactly the same representation. Fortran is a bit old-fashioned, so you have access to the binary representation of the corresponding number, so you have to interpret it. One of the nice points is, depending on your compiler, you may have a different representation for the decimal number that is printed out by Fortran. But this binary representation should be the same whatever the compiler, at least if the compiler has not changed the computation itself. But okay, when you have a constant value, the binary representation here in hexadecimal should stay the same. Okay, you can also do it in Python with the trick that when you say float, you mean double, but the same things appear, so nice. In Ada language for the happy fuse. And to be honest, you can do it in Rust, but as I didn't find a proper library, I had to encode it by myself using the bits of the corresponding representation. So we have no excuse not to use this kind of representation. What it means is the interface is a leaky abstraction, because you can access the detail of the encoding of your floating point number. So it's a bit as if you considered your integers, your float, I mean, as an object with 3 components, the sign, the mantissa, and the exponent. So be it in C, C++, or other languages, you can extract the fraction and the exponent. You can load some value for the exponent you want. You can rescale your mantissa and the exponent. You can access to the numeric limits, the number of digits. So your object is showing up whatever details of implementation it has. A small detail, as we will see next week, some aspect of vectorization, this C API that gives you 2 results for one number doesn't vectorize well. So you might need to use the dirty way of playing with the bits to express performance with vectorization. Of course, not in Fortran, where exponent and fraction release only one result and should be properly compiled depending on the compiler. Okay, so let's start with a simple traumatizing example when your colleagues come and say, oh, I asked the computer what is 0.1 plus 0.2, and it's not 0.3. So we'll compare the sum, sigma, and the expected result, C, by computing some discrepancy A plus B minus C. So, sorry for the small size. You can find the slide on the site. When we express enough decimal digit of the number, we see that there is a small remainder at the end of all our digits. So we have the 4 lines of float, single precision, double precision, long double, and half precision. And what we find for the floating point number is that the inaccurate representation that we get corresponds to the sum of the inaccurate representation of the two terms. So it's false, but it's consistently false. So it's not so bad. When we go to double, it should be better, or at least as false as. But in fact, we get the sum of the inaccurate representation being different from the representation of the sum. So it's not good. And we get a small discrepancy of 10 to the minus 17. So maybe it's not so big of a problem. Long double makes it half correct as for float. And yes, half precision is not good. We all knew it. So the problem comes from the point that decimal number, the one that we use every day, are not binary number. So we'll have to see more into detail what defines this kind of number. In turn, it makes binary conversion needing some rounding. 1/5, which is 0.2 in base 10, when expressed in base 2, has an infinite sequence of binary digits. Because of this, when you truncate to 23 digits, it means that you introduce some uncertainty. And you encode it in memory in this way, which is 0.2 plus something 10 to the minus 9. Okay. So we should stick to integer, as said Kronecker, but okay, we have to use a decimal number. Okay, so what can we say about decimal number, which are, as we know from junior high school, some integer over a power of 10. In fact, binary numbers are almost the same thing, some integer over a power of 2. But for instance, so as a consequence, all binary are decimal, but some decimal are not binary, because 1/5 cannot be expressed as a finite sequence of binary digits. Okay, so consequence, don't use floating point number for financial computation. You will introduce fractions of cents everywhere, and your boss will not be happy. What do we have with these sets? Either the decimal and the binary. We have the closure. The sum of binaries are binaries. The sum of decimal are decimal. The product of binaries are binaries. The product of decimal are decimal. We have commutativity, associativity, distributivity, total order, and the topological aspect that even if binary are a very small subset of the real number, we could, in principle, get arbitrarily close approximation to real number. If only we had an infinite number of bits, but we don't. So I introduce yet another set, which is F for the finite floating point number. These are binary numbers, but with a finite number of digits for the mantissa. And then we start losing things. We lose closure. So it means we need to introduce rule for rounding. And we need also to extend our set to represent infinities not a number, -0, in order to deal with overflow exception, underflow exception, and inexact exception. Basically, everything that you can compute with a finite number of digits has a rather high chance of being inexact. When you have to truncate the exact result of the computation between two representations, you will lose digits to rounding. Basically, to make an exact product with 23 binary digits on each side, on each factor, the result will have 46 binary digits in your multiplication. So you have to lose a big part of them. Okay, we managed to save commutativity, which is very nice. But as we lose associativity, when the compiler will decide to compute things in a different order, or when not simply commuting values, but changing the order of sums, changing the order of product, or when you will multi-thread your code, and then the order of the reduction at the end will not be the same, you will not get the same result. So you have to be prepared to this. Okay, we keep the total order, except for not a number that are both smaller and bigger than any other floating point number. And as for the topological aspect, as they are a finite part of the binaries, they are dense nowhere, and we cannot do much with them. So getting into more detail about rounding, the idea is you have some curly x, that is your real number that you want to represent in the computer. It falls between the two closest representable neighbors on your floating point line. And in principle, you want to select the closest representable number, in this case, x plus. So the quantum gap between two closest representable is called 1 ULP, unit in the last place. So the best you can ever hope for is getting your number within half an unit in the last place. This is what we call correct rounding. Sometimes it is difficult because it supposes that you can compute with more digits than in your representation. So it's not so easy to be sure that you have correct rounding, as we will see. When you get within 1 ULP, we speak of faithful rounding, but most of the time, most of our computation are happy-go-lucky rounding. We are not sure of anything. One thing to keep in mind, it's nonlinear because we have threshold effect. We cut and get different value between here and here. It's nonlinear, but it's completely deterministic. So we have introduced this notion of ULP on the so-called machine epsilon. I will stick to the mainstream definition. This is the distance between 1 and the next representable floating point number. And by shifting, by any kind of multiplication, you can have the number you want on the next representable number by multiplying by the number you want. We can also think of it as 1 ULP after 1, the machine epsilon. Or equivalently, the largest relative interval between two nearest numbers in finite precision. And the typical value of this machine epsilon moves from almost 1 in 1,000, 2 to the minus 10 for half precision, up to 10 to the minus 34 for the quadruple precision number. So it gives us a rough measure of how close two floating point number can be before they merge into the same representable value. In some sense, this is the resolution of your computing instrument. Like in experimental science, we have a resolution. Okay, so every decimal is not a binary. So when we type a literal floating point number in our program, it will be converted for the computer, and we will lose something during this step. The compiler will fool us. The math library will fool us. We had better be prepared. As it relies on rounding, so I provide you with some example for 1 inch in millimeter. Nobody will get the same value depending on the accuracy. But on the opposite, we are sure that every binary is a decimal. So there should be no problem. But if you want to express completely, exactly your binary, let's suppose that we want to represent 1/8, which in base 2 is the first binary decimal would be 1/2, the second 1/4, then 1/8, okay? So in base 10, it's 0, 1 to 5. Up to there, no problem. But if our resolution is limited to 3 binary digits in an imaginary floating point format, it is meaningless to express this 2/100 and 5/1000. The only meaningful result you can display is 0.1. So if you were asking the compiler to display exactly what it has in memory, all your values would be twice as long. But the second part of the display would not be meaningful. So we have conversion to binary when we input a decimal number. We have conversion to decimal when we are back from displaying the result of our computation to the screen. As a consequence, please don't have back and forth. For instance, my first program put decimal value in a file so that the user can check what it means. And then the second program will read the decimal value. Maybe it is a different library, maybe it's a different conversion. And you introduce some error. And if you have many cycles in this way, you can get false results. Please have your data in binary format for any serious operation. If decimal is really a must for what you are doing, you have options. Starting from C23, we have decimal floating point. So all that I said today mostly applies to binary floating points, as they are the most common and most speedy format. It's in silicon. Whatever is in decimal is not as fast, but you have always a choice to also program in SQL or COBOL. And as I mentioned, elaborating from this C23 version, I made a thin binding to Fortran, and we will see some results. Okay, so you can use also technology called fixed point, or have all your money counted in cents with integer number of cents instead of decimal number. Okay, so it turns out that this has effect. Pi has no rational representation, even less a floating point representation. So when you compute the sign of pi, the exact should be 0. But here you will see something which is of the order of some machine epsilon. In FP64, the same goes, but you have a smaller machine epsilon. On FP16, okay, I had to trick the computer into using the single precision sign because you can do mostly arithmetic with half precision. Most of the functions are not ported to this precision. Okay, so you have the same kind of result. And if it is really a problem, this small discrepancy in radian, you should use half-turn trigonometric function that exists from C23, sine pi, cos pi. So this function rely on not simply multiplying sine of pi times x. They are better elaborated so that you don't have this kind of problem. You can also use trigonometric function in degree that exist in all good Fortran compiler and that are part in the next level of the Fortran norm. Okay, so let us see another problem that appears with this floating point number. When you have some series, you sum the inverse of the reciprocal of the integers up to big N of 250. So I chose a half precision number because I don't like them. And when you sum from the bottom up, from 1 to 150, you get this result. Whereas when you sum down from 250 to 1, you get already a different result, which is closest to the theoretical sum. Okay, this theoretical sum can be evaluated with this asymptotic formula. And then the discrepancy gets bigger and bigger between the up sum and the down sum, which stays close enough to the theoretical sum. And at some level, the upward sum is not moving anymore because you are pushing numbers that are smaller than the epsilon machine. So you are summing up two small numbers for them to have any effect. Even the down sum starts failing to increase after 8,000 for n. So don't forget that this sum is diverging, so we should be able to go to infinity. Okay, and so we see the discrepancy here with the theoretical sum already for 1,000. Whereas with a single precision, you can go nicely with almost no effect to 32,000, here where it failed, and you hardly find any discrepancy for the up sum in up to 3 million. Can we improve on this? Okay. I gave this example in modern Fortran, but don't hesitate writing it in your favorite language to express the sum. And we will replace the classical sum that we had here in this way. We'll replace it with the so-called Kahn-Babushka summation. So Kahn was Professor Kahn we have seen at the entrance. And with this trick of compensated sum, we get the following result. So I took the same up sum and down sum as before. I mentioned the point where the sum start failing, and I computed a Kahn up sum, which fails only about there at 6,400,000. So 64 times further than the classical up sum. The Kahn down sum also fails at the same point. So when you use the Can trick, you don't need to rely on the ordering of the sum, which is nice. If you have a lot of numbers, you will not keep them in memory, sort them, and then sum them up. You can have to do it if needed, but it would be very costly. So please use a Can summation when needed. In order to compare values, double precision number go much further without needing this sum. So sometimes you may think of what the hell? Why should I need double precision? Nobody needs 16 digits. But here, it shows some interest. Okay, so before going further, we'll consider all the levels of complexity that we can have in our computation. We have the basic level of arithmetic, plus, minus, product, division, and all kinds of integer power. Then we have a second level of algebraic operation with the square root, the nth root, all kinds of fractional power, and even all roots of polynomial are of algebraic nature, even if we cannot express them with roots after degree 5. Then we turn to the so-called elementary transcendental function, all exponential, trigonometry, irrational power, and even higher transcendental functions, so-called special functions that our fields of application are full of. Okay, the correct rounding is only guaranteed by the standard for arithmetic and square root. But be ready for some breaking news. Okay, so for all the rest, transcendental functions, they are costly. They take a lot of arithmetic operation to evaluate some approximation. And as we have seen, their correct rounding is not guaranteed. Why is it so? Okay, so we saw that the rounding is nonlinear. It is, in this respect, mixing various scales of your computation. And you can start runoff, the equivalent of butterfly effect for everything nonlinear. So to get the correct rounding with so many bits, please look at this paper. We may need 32 digits of computation, quadruple precision, to have the certainty to round it properly. In fact, here, as we are a smidge above 5, it will turn this 9 into a 10. In the same way, here, we need to go rather far to be sure that it will not round up this 9 here. Okay, so this also speaks of double rounding. Sometimes you may see, okay, I have some very hard computing problem that requires higher precision. I will compute it in a long double, and then round it to double, and then round it to float. But then this can also give a worse final rounding than expected. Breaking news. Library 241, the glibc 241, was released this year. Now, the team of Paul Zimmerman guarantees in C correct rounding for the transcendental function in float and double. This is a good news. This is also a very bad news. A lot of your colleagues will come to your office. Oh, I don't understand. My program is not putting my result as before. So get ready. Okay. So I was mentioning double precision. But what physics need double precision? What physics, beside quantum field theory and the muon magnetic momentum, magnetic dipole needs more than 6 digits? Okay, so let's have, sorry. Let's look at the famous Stefan constant, the ratio of the total power radiated per unit surface area to the fourth power of absolute temperature of black body. It's some combination of pi, the celerity of light, the Planck constant, the Boltzmann constant, and it is expected to be this value with the most recent measurement in NIST. So let us compile it applying the standard formula. And with another variant of this formula here. And the result in single precision is none. If you express it because somebody else has computed it intelligently, you will see the expected result, 670, 374, 439, 419, okay. So we are a bit off, but we are correct as far as single precision is concerned. So why did we get not a number? Any idea? Okay, so let's compute. Here we have Boltzmann to the fourth. So Boltzmann is something like 2 to the minus 23. So to the fourth, it's 2 to the minus 10 to the minus 92. Ooh, this is 0 for floating point number, for float, single precision. Then the light speed, the Planck constant here to the third is minus 112, so it's 0. So you have 0 over 0. That's it. You are computing not a number. So please don't dismiss double precision too early. You can have surprises. Of course, you have understood that half precision floating point number will suffer a lot. So let's see what it gives. They are implemented in NVIDIA Fortran, not yet in G-Fortran or IFX. So all the compiler gives the same result when you stick to single precision, but for half precision, even the more intelligent way to do the same computation when you mix some Boltzmann and Planck constant together so as to mitigate the uncertainty, it makes it none as well. Because with this precision, C is infinity, H is 0, and K is 0. So don't be too eager to use half precision. It may not apply to your field. Okay, so let me address the main point of today, which is what we call catastrophic cancellation. So this slide here is in base 10. We imagine we have base 10 floating point number. This is an imaginary floating point number format with 3 decimal digits. It would be the half precision decimal number. And so we have some exact representation for 3.34, and B is 3.33. You can express, so this symbol is a minus, and the circle means rounding. So all operations in your computer are classical operation rounded. So the result of this computer operation is 0.01. So this is a cancellation because we had 3 digits for each of the terms. We have only 1 digit for the result. We have lost some data in some sense. But this is a benign cancellation because the floating point result is the exact result in this case. Okay? And now we compute the difference of the square. So if you do it exactly, you will find 667 10 to the minus 2, which can be represented in this format. But when you do the way a computer would do it, rounding the product of A, rounding the product of B, and rounding the difference, you get 0.1, which is 1.00 10 to the minus 1. So we have 50% of relative error on the result, which we can also describe as 333 units in the last place, and no digit of the displayed result is even correct. In this case, we speak of a catastrophic cancellation. And we have two questions. When does this occur? How many digits are lost? And we have no way to find it. On top of this, we have an overflow risk, not with this example, but we are taking the square. So for high enough number, representable number, we may have the square of A not representable, the square of B not representable, but the difference would be representable. Okay, so some trick is to use as much as possible factorization. You know the Fein formula, A plus B times A minus B. And in this case, it provides us with the exact result. So this is the right way. As far as possible, try to factorize things. Every year, somebody asks for the same question because you cannot reproduce the last page example as there is no such decimal floating point format. So in binary, with FP16, you have a mantissa of 10 binary digits. And if you take this number that has some exact representation in floating point at precision, and this other number, and here it's the rational representation, you do the same operation, and you get even 422 units in the last place of discrepancy. Whereas when you factorize it, you get within 0.35 units in the last place. So you have the correct rounding. So let us stick to factorization as far as possible. So we have seen catastrophic cancellation. So now we turn to the cursed cancellation, the one you cannot do anything about. So we have some very nice formula. These numbers are not very bad. We have a polynomial in two variables, x and y, up to degree 8, plus some rational fraction, x over 2y, with x and y, two integer numbers. They are representable. This example is from Siegfried Rump, who is famed for this kind of intricate example. You can find the paper. And we compute it in float. Please implement it in your language of choice. And we find minus 6 to the 10 to the 29. Okay, so we compute it in double, and we lose 8 orders of magnitude. Something seems fishy. And we turn to long double because we pay for it for 40 years, and we have yet lost many orders of magnitude, and the sign has changed. Something is very fishy, so let's turn to the tool for professional. In quadruple number, we have lost 17 orders of magnitude, and the sign stays positive. What? Okay, FP16, I don't like them, not a number from start, okay, nothing to be done. And the exact result can be represented as a fraction, as you can see here, and it's a negative number less than 1. So even quadruple number could not get it. And if you take this representation and you compute the result from this representation, you will get something even in half precision that is not so bad. You have 3 digits, should be okay. Not one of this computation has 3 digits, not even the sign. Okay. The result can be represented in any precision. The result can't be computed in any precision. What can we do? Okay, so I told you about decimal floating point. And recently I played with my Fortran binding to the C library. And then I got for single precision decimal number, -4,000, 10 to the 30. So, okay, it's compatible with the float, the single precision binary. In double precision decimal, I have 3 10 to the 21, -3. So the sign stays the same. The order of magnitude stays the same. And the quadruple decimal precision is like the quadruple binary precision. So there is something. We see that in decimal, all these numbers are 0. We have only one significant digit. Okay, not for the quadruple precision, but we'll see to it. Shouldn't we look at the binary digit of our computation? Okay, so in binary, single precision, double precision, and double extended, we also have only one bit of mantissa. It means that all the digits canceled. So when we see this result, we are lost. But in this case, please take a look to the binary representation, because it can tell you that something has disappeared. It's not a guarantee. Here you see the long double, they still maintain some digits. The quadruple, they have a lot of digits, but something fishy is happening. As we are looking into the detail, this quadruple value, be it in decimal or in binary, is exactly what you get from x over 2y. It means all the polynomial part has disappeared. Okay, so let's look at the polynomial part. So this is the initial definition. You can see that you have integer coefficients. 1/4 in binary, it will not be a problem. It will be a shift of the exponent. And we can even look at the fact that all the powers are even. So can we factor this polynomial? This is not an obvious question. So I used the Macaulay symbolic algebra program, and I try to factorize it with the real, with the complex, and in the projective complex space, as we can see that all the terms are not of the same degree. So sometimes by introducing a third variable, we can have everything on the same degree and express a better thing. But Macaulay told me no, in any case, be it with this simplified degree or with the usual degree. So in fact, in some case, we will be stuck. And it will not be obvious to understand why. So we can now address a simpler case if we cannot address all the cases. When you evaluate one variable polynomial, here we know that at least on the complex number, we can always get some factorization. And in the real number, some of the factor will be x minus some root, and some other factor will be maximum second order. So factorizing a polynomial means finding the roots, and it's some work. But if it's needed, we will do it. But if it's too complicated, we can use this expression where you start from the higher order coefficient and you compute a(n minus 1 plus x times a times x plus the former coefficient times x plus the other coefficient until you get to a0. So some people say you have a gain in speed because you are saving on the operation, you take a lot less powers. With FMA here for a(n minus 1 plus x times an, you have a gain in accuracy, partly for the same reason. But most importantly, you have the guarantee of stability. So this Horner scheme is the way to evaluate all of your polynomials. Don't do it the naive way. We can go even further with adding a compensation summation techniques such as the Kahn-Babushka we have seen. This kind of problem applies to all statistics. We are scientists, we compute a lot of statistics, variance in particular, which is a difference of square of sum on sum of square. So many things can go wrong. We lose accuracy in the sum. The difference of square is also ripe for a lot of catastrophic cancellation, and you have two solutions. The two passes approach, where you first compute the average, you take it off the number, you shift them to the average. If you find it too expensive and you have already some idea of the average, you can arbitrarily shift your data towards some expected average value. And then you can go to the Welford algorithm page and get some explanation, more complicated, more computationally intensive, to get the best result possible in one pass. We'll soon have some intermission, but okay, so for typical computation will be dot product or equivalently convolution product. Fourier transform, matrix product, we have seen they have a nice arithmetic intensity. On all these turns out to be a sum of simple product, quadratic in essence. So we expect to see the same kind of problem that we have with the variance. And we can't use the factorization trick for all these aspects. So what can we do? We can go to higher precision to mitigate the uncertainty. We can use FMA, fuse, multiply, and accumulate. We can use it in a way to extract exact product. So I don't enter into the detail, but I can elaborate if you want. And it can be combined with Kahn or other compensated sum if it's really needed. Okay, so before some intermission, one of our problems in many codes are comparing floats. On most of your compiler, with the proper warning, will tell you, oh, this is bad, you are comparing floating point number. So when we are comparing number, a equal b is equivalent to a minus b equals 0. So we want to get a manifest cancellation. In order to compare, we want to provoke the ultimate catastrophic cancellation. On the number we compare are full of error. So when we want to compute this mathematical difference, what we are computing is the rounding difference plus some uncertainty of rounding, plus the uncertainty of representing the real number to the floating point number, minus the uncertainty of comparing the other number. So when you try to check in your program a equals 0.2, you have a representation error, at least on the literal. Will it be better if we compare 5 times a to 1? Okay, 1 has no representation error. But if a is supposed to be 0.2, it has the representation error. So this is not a solution. Okay, when we want to compare something to pi, it will not work. Pi has obviously a representation error, so the number that represents pi in the computer is not the right one. And when we want to compare to 2, it cannot be simpler, but we have representation rounding the error on A. Okay. What is more, we speak of error, but you know there is absolute error and relative error. On floating point number, always, for floating point number, we always speak in terms of relative error as their representation is a product. So in comparison with an absolute threshold, it's not the most relevant. So when A equal B, the absolute error would be IPSA, but this IPSA cannot be arbitrarily small. And for relative comparison, we should use this error of an expression. We want to be at some level. This epsilon is not the epsilon machine. In the best case, it can be the epsilon machine. But you have, depending on your problem, to select your level of accuracy for equality. And then this value being relative, it has to be multiplied by the absolute value, the max of the absolute value of the terms. In this way, the formula is homogeneous because your epsilon, or the epsilon machine, if you so choose, are dimensionless numbers. Things get even more complicated when you want to compare to 0, because you cannot use the formula we have just seen. A equals 0 means absolute of A being something times absolute of A. It will be difficult. It will never work. So in the case of comparison to 0, then we are back to absolute uncertainty. And even if it's not epsilon machine, so the eta can be arbitrarily small. So for each kind of floating point, you have some value of epsilon machine on some tiniest number that you can represent, and they are not the same. On the tiniest denormal is in fact epsilon times tiny, tiny being the smallest representable normal number. Sure. Sorry. Okay. Okay. how do the limitation quarks of floating point precision affect modern machine learning models and tools? So if you wait for another hour, I will address this topic. So maybe I would like to finish this part on. I will be glad to say a lot of bad things about machine learning in this respect. Okay, so we have been speaking a lot of unit tests. On comparing floats is a difficult topic with your unit tests. So it forces us to think about what we really want to check. When we want to test that A is 0, it can be a part of our test. Is it meant to avoid computing the reciprocal? What is the goal of this test? If we want to check that A is bigger or equal to 0, is it to avoid computing the square root of A? So is the test meant to check for the domain of the function? If we want to check that some value is below 1 or maybe equal, is it to avoid computing some arcsign? Because the equality part will not be meaningful. We know we have to give some slack. So we have to really think about what is this unit test. Unit test expected value of a function at a given point. Also, we can have tests that check for non-representable value. So we have to give some slack to the computer. So I addressed the hot topic of today with denormals, and I want to thank a lot my colleagues on the last row. So as we have just seen, we have number between tiny and epsilon machine times tiny, which don't have a full representation. So here are some values that are given for this range of value. So you see that half precision floating point number have really floating point denormal range in the range of number we could use, even us human. And these denormal numbers are really needed to get your mathematical algorithm to work properly. When you are factorizing matrices, when you are diagonalizing matrices, we need them. It would be worse than if we had not them. But why not use this number? So Pierre was the first to run some tests with some computation where you increase the number of denormal data. And he has shown that the time spent per element depended on the fraction of denormal inside your collection of data. And when you were at 100% of denormal, you were 100 times slower than when you had no denormals. Yes, okay, but if we do our computation in double, we will not have denormals. There are 10 to the minus 300. It doesn't exist, this number. Would you bet? Okay, so it's time for some video. So here are movies of the Gray-Scott reaction produced by the Magic, the Dream Team. So you have already seen this standard image of the Gray-Scott diffusion reaction propagating and moving nicely around. But Adrien remarked, because instead of playing the result, he was playing it while producing the computation, that at some point, this nice display would slow down. So we took a lot of thought to it. Sébastien has produced a video where we see the denormal numbers here. You have a front wave, a shock wave of denormal number that propagate in advance. As they are so small, we cannot see it on display, on the normal display. So here the two displays are stuck together. And you see that there are two fronts. In between, you have something mixed of result. Then you have a second set of two fronts. And the point is that this denormal number, they take much more time to compute. So this is why Adrien observed this problem. You see your ring of denormal numbers taking more and more size, and so taking more and more computer time. Why such tiny things? Shakespeare would say much ado about nothing, but here we are. Okay, so before the next transparency, here are some results from Pierre and Sébastien. So you see on the x-axis the number of steps. We have 1,000 images. You can look at the, is it orange, this line, dotted line? Sorry for color vision out. And we see this represents the number of cycles per cell. So the rendering, when the times move on, we get from less than 4 cycles per cell to more than 6. The time is getting bigger and bigger. We need more and more time to do the computation. Okay, so let us count the number of subnormal. This is this wiggly line here. And the number of denormal, as we have seen thanks to the video, is getting bigger and bigger. And then at some point, there is not enough room, so the number of denormal is getting less and less. So why then is the time spent growing bigger and bigger? So they have been looking for the number of 0, the number of pixels with 0 value. Because when your computer sees a 0, you can say, multiplying by 0, okay, I pass. And then it takes less time. And the number of 0, which are most points at the start, is consistently decreasing. It means that the number of opportunities for the computer to not lose time, is decreasing, and so the speed is decreasing. Okay, so some idea was to shut down the evaluation of the normal number. You can do it with some control register of your CPU. Don't do it, okay? It looks nice. So this is this blue dotted line, sorry, this one. And in fact, it's almost not affected by the number of the normal pixel. Okay, so there is a lot to explain and to check on this graph. So the point is to get you aware of where insignificant values can lead you to. It should not have any consequences, and it can get you to lose a factor 2 in speed. And in this case, maybe in other cases, it can be even worse. Okay, but this is an Intel chip. This is an AMD chip, so you recognize, you get the same number of denormal, you get the same number of zeros. So the results are consistent, God thanks. But when you check the subnormal on the computation done without taking into account the subnormals, the AMD chip is almost not affected. We are at 4.5 cycle per cell, so okay, it's a different processor. It's not the same founder, but okay, we have from 4 to 4.5, but AMD processor will not suffer from this aspect. So I told you about the number of zero in the plot. So here you can see in the pinkish way the zeros of your code. So when the reaction takes place, the concentration gets bigger than 0. And you see this front of mixing between the normals and 0 here. And then here you reach inside the realm of meaningful numbers. So can I continue for 5 more minutes, or should I leave it for today?
You can continue for 5.
Okay, so let's have some math. Up to now, it was just computing, you know, but so we want to think about it. Okay, sorry, so we'll be looking at simpler equation first. So we have the Laplacian of u being the square of the Nabla operator. It plays in two big categories of equation, the wave equation, such as the D'Alembert equation. So here you have the c squared, of course. So you can see that this as the D'Alembertian operator. What it has is second order in time and second order in space. On the other hand, we have a diffusion equation in Prescott, so closer to the Fourier heat equation with first order in time and second order in space, where, okay, for the heat equation, this coefficient alpha is the so-called thermal diffusivity. And as these equations are linear, contrary to Prescott, we can go further in the solution by using plane wave. with some vector wave number vector on some pulsation in time. And so the wave equation translates to, okay, the C-square is missing everywhere, sorry. So we have the so-called dispersion relation here that makes the propagation equation lose intensity of u as the square rule when your wave is expanding from one point. On the other hand, when we solve the dispersion relation for the Fourier heat equation, we get something more complicated. Your wave vector becomes a complex number with a real and imaginary part. The real part gets you a sine wave. The imaginary part, because we have the two signs, on the physics makes the expanding exponential not be represented. The last aspect makes this sine wave decaying exponentially, like the temperature when you go below ground is not affected by the daily oscillation of the temperature on the yearly operation, modification of the temperature. So this comes from here. So it means that the linear part of our Gray-Scott equation will have some decaying exponential. And this decaying exponential is what brings your result to lower and lower value. And this lower value will get in the denormal range. So we have one aspect of the explanation. Another aspect is that, okay, your sine wave of the linear part of the Gray-Scott equation, they are here, gives you small enough values that will get squared with this term. So not only the linear part is getting us small value, but the nonlinear part is getting us value getting small very fast. If you have at some point a concentration of V 10 to the minus 18, at the next step, it plays in here with a factor of 10 to the minus 36. So your floating point number in single precision have no way to get out of this. So as you see, there are still a lot of things that I would be glad to discuss, but I have benefited from your patience. And I can take some question or maybe elaborate on the question of our colleague about machine learning. Thank you. Should I address the question of okay, so the slide is ready, so why not use it? Okay, a big part of our activity in computing for science is what we call fit. We have some model, and we have some data, and we try to find the best fit. And we usually do this with a minimization algorithm. So we have cost function that depends on all the parameters of our program, and we would like to evaluate the discrepancy between the data and our model. And next to the minimum, every function next to its minimum has the same structure. It is a quadratic form because you have here I took a simple function, simple parabola, depending on only one parameter. So next to the minimum value, it will have a value at the minimum. The derivative will be 0. And you have a quadratic formula around. And what I displayed here, the red points are evaluated in double precision, and the blue points are evaluated in single precision. So when you get close to the minimum of your function, if you evaluate your function in single precision, you see quantum steps. Their I of their H is 1 machine epsilon. As their H compared to the minimum is like the square of your how far you are from the real minimum, it means that the size where all of your value cannot be separated will be like 2 square root of epsilon. Okay, so epsilon machine in single precision, it's 10 to the minus 7. Square root of epsilon machine will be like 10 to the minus 3 and something. Okay, so we have lost 3 digits. We cannot, if we check for the minimum of our function in single precision, we will not find the exact minimum within more than 3 digits. Okay, it depends on the coefficient of your quadratic formula. So you have some margin from improvement, but not much. So whenever you are fitting, particularly in a very high dimensionality space, you should always aim for the largest resolution that you can afford and not get to single precision. Is there something below single precision? Ah, yes, half precision. So if I compute with half precision, my square root of 10 to the minus 3 is 3 to the minus 2, 3%. But who would dare compute a minimum in floating point, half point, half precision? People in machine learning. Okay, does it answer the question? I leave it to you. There is this paper already 6-year-old where they attempted to use machine learning to solve a quadratic equation, which would have been the part to discuss later at night. So, as for the other question, is it possible that rounding error appears for integer? No. If you have computation only with integer, you can have very bad thing happen. If you overflow, nobody tells you that you have overflown. This is the worst that can happen, but this is not rounding error. Thanks, Adrien, to have already replied to this. Any other question?
Can you make some tricks, for example, in the slide in the beginning where you were calculating some very small constant and the speed of light, which is like very large constant? Can you like compute this in double precision and then round it to a single precision and continue with this number, not having to do double precision all the time?
Absolutely. in some point, we can use mixed precision.
Yes, if you call it like that.
It saves the day. So the takeaway, okay, so here is the final takeaway. Precise number plus precise number is a slightly less precise number. The same for multiplication. Precise number plus garbage is garbage. The same for multiplication. Square root of garbage, less bad garbage. Square of garbage, even worse garbage. A number of pieces of statistically independent garbage is a better garbage. When you go to the power of a precise number to garbage, it's much worse garbage. The exponential is here. Garbage minus garbage, we have seen it, much worse garbage. Okay, the only way to get precise is multiply by 0. So this is the XKCD. And so what I wanted to, okay, so with more time, I would have demonstrated CANA, which is some stochastic arithmetic that will do the same computation with rounding stochastically changed to rounding to infinity to rounding to minus infinity. And then you are constructing a kind of drunken walk that have your, you get 3 copies of each variable, but each of the 3 copies is randomly computed with a different rounding at each step. And this allows you to see in the end what is the average rounding error that you have with this. And so you should not see after this talk precision as something fixed, but this is some life insurance. If you are in double precision, you have 53 bits to lose, whereas in single precision, you only have 23. And in floating point, you have nothing to lose, so it's worthless from the start.
I speculate that the n pieces of statistically independent garbage equal better garbage might answer the question about why machine learning can get away with using less float,
Yes.
less precision.
Yes, it has a lot to do with it. So I have not addressed the issue of FP8, FP4, or FP6 in between, but they work seriously on checking that it's okay enough for them. And the idea is the result of your machine learning will tell you there is more probability to be in this class than in this other class. I don't know, except the guy from which I have shown the poster. I don't know anybody using, yes, I know people, but they should not do it. Using machine learning to compute some value. Usually they use it to classify between some value. And then the amount of defect that you get from not getting into the right class is less big than the error that you would have on some continuous value.
Yeah, sometimes you have very large number of classes though.
Yes. So I'm not really knowledgeable about machine learning. So I don't know what amount of projects are using half precision for the quick inference, and if people are really using half precision for training. So if you use single precision for training, it's costly, but okay, you save a lot of numbers. lot of accuracy.